Hi, this is Richard Gibson. In this tutorial, we will build on the results shown in the previous video where we had calculations for a simple, small tensile fracture of a fixed size. In that previous session, we showed the displacement and strain values generated by the fracture and compared them to field data. The basic model helped us to get a good starting intuition for explaining some of the most important features observed in low-frequency DAS data that are acquired in hydraulic fracturing projects. However, there are a number of details that we need to add to make it more complete. And in this tutorial, we'll take the model, make it a bit more elaborate, and then show how we can use it to model strain data generated over time by a propagating hydraulic fracture system. The result will be to help us understand the DAS data even better. To start, let's do a quick recap of the data example from the HFTS2 project. We did describe it in some detail in the last video, so I'll just touch on the main points now. In the part of the illustration on the left, we see the well 4H, its trajectory, which is the treatment well where the hydraulic fracturing was carried out. 3H is the monitor well, including the fiber optic cable, and that was used to record the data that we see on the right. And for today, we're going to continue to focus on the part of the data which is inside this black box here, and it's the data recorded before the frac hit takes place. This part of the data thus samples the behavior of the rock medium when the fracture system is still some distance away from the monitor well 3H. And the primary feature that we want to focus on is this reddish heart-shaped signal with its two lobes. And again, this is indicative of that deformation induced by the approaching fracture system. To expand on and build upon our model, we're going to take this as a starting point, the simple model from the last video, and expand on it to show how the strain field varies over time as the fracture system approaches that monitor well. In the map view figure here on the left, the horizontal axis is the east-west coordinate, the vertical axis, or Y, is the vertical axis. In the middle, we have the treatment well in blue. The monitor well is shown on the right in green. That's where the fiber optic cable would be located. Here, I'm showing a small red line that indicates the position of a newly opened fracture as it propagates east and west away from the treatment well. It's a vertical fracture, and the bright green arrows above and below show the sense of motion of the fracture surfaces as it expands. Here, in the figure on the right, I'm showing the strain field, which is induced by this small fracture section along with the same well and fracture lines. There's one point that's a little bit tricky here. You do remember perhaps that there are 6 unique strain values in general, but just to be clear for completeness, I want to note that I'm showing the strain value in the map view figure that would be detected by the same north-south fiber optic cable as indicated by the position of the monitor well on the right-hand side there. The next step is to go from a single small fracture of a fixed size for which we can easily compute strains to a propagating fracture of a changing geometry. We also need to start thinking about fracture height. To show this a little bit more clearly, let me go ahead and run this movie here on the left. And what we're seeing here is a fracture rectangle, again, simple geometry just to make it easy to work with, but that fracture propagates in both directions away from the treatment well. And we see that it eventually, in most cases, or at least many cases, will intersect the monitor well. Now, to expand our previous calculations from that small individual fracture element to this complete fracture surface, in principle it's straightforward. We can just take the results in the previous video and integrate over that fracture surface as it expands. However, let's make this a little bit easier and faster to work with. I'm going to make a simplification. Specifically, as we carry out the integration, we're going to apply it only to the fracture tip or edge, which is this dark red region showing on the portion of the fracture which is approaching the monitor well. And this is okay to do as a starting point, at least, because we've already seen that the strain induced by the fracture decreases in amplitude very rapidly with distance. The portion of the fracture that's located on the side of propagating away from the monitor well, there's going to be so far away, it's only going to create a negligible influence at the fiber location. And furthermore, we're going to assume that most of the strain isn't created by that newly opened dark red fracture tip as it approaches the monitor well. So really all we have to do is integrate over that dark red vertical strip, that approaching fracture edge or tip. So let's summarize these ideas and clarify a little bit of terminology too. When we used our previous result to compute strain for a small fixed size fracture, it's strictly speaking a static or a constant value. Our data, though, show that the strain changes over time. So conceptually, we're going to apply what we'll call a quasi-static model. Over a relatively small time interval, something like 30 seconds here, we can treat the response of the slowly developing fracture system as a static result. Okay? We can do the same thing for the part of the fracture that develops in the next 30 seconds, and then the next 30 seconds, and so on. So in the end, we have what we call a quasi-static solution. For today, we're also going to assume a constant height of the fracture system, 30 meters, just for simplicity. We're going to assume it propagates away from the treatment well at a speed of 1 meter per minute, which is reasonable. We're also going to keep it simple by taking the monitor and treatment well depths as the same, remembering that we're focusing only on the horizontal portions of the wells. Finally, as noted, we'll compute the strain from the approaching fracture tip only, that is 30 meters in height. Here, we show the model strain in the map view on the left. Time 0, there is no strain because there's no fracture yet, so everything is 0, or the light green color. And the treatment well, again, is located at x equals 0, with a dark blue line showing its position. The dark green line here on the right shows the position of the monitor well in our hypothetical fiber optic cable. And on the right, there's a heat map display showing the modeled data over time. And during the animation, this light white line here at the left will scroll across to show you the time value corresponding to the data which will be shown on the left. So start the movie, and we see this fracture propagating towards the right, and so this strain pattern just propagates to the right along with the fracture tip. And so as it approaches and gradually intersects our monitor well location, we see the development of the heart-shaped signal. So let me show it just one more time. And so again, we have these positive lobes of strain induced by the fracture tip, and as it gets closer and closer to the fiber optic cable, we start to record those patterns here until we see the development of our heart-shaped signal. In this tutorial then, we've taken the static model building block results from the previous video and shown how we can create a quasi-static simulation that helps to understand how the strain field propagates through the subsurface and how the moving positive strain lobes create the heart-shaped signal that is often seen in low-frequency DAS data. However, we are still leaving out a lot of information and a lot of variability in the subsurface. In reality, for example, the two wells are often at different depths, and this is certainly true for the HFTS2 data. This needs to be considered down the road, as does the impact of fracture height, which will generally change over time as well. So we've made some good progress, but upcoming videos will continue to build on these results to help address some of the open issues. Thanks for watching.